In this review, I am literally going to try and break this inverter. I am going to try to kick on the protections, whatever I can do. I've got some nasty resistive and inductive loads. I've got 4 space heaters hooked up to this thing. We're also going to analyze the sine wave on this inverter and see if it's a true pure sine wave inverter, especially under load. Cheap inverters, the sine wave will get all wacky and noisy under load when you're putting it under a kind of load like this. So I'm really curious to see what the sine wave looks like with all this load on this thing. I'm gonna break it open. We're gonna thoroughly analyze the circuit inside. We're gonna look at its weak points, analyze the efficiency under full load. We're gonna hit it with the thermal imaging camera, and we're gonna see what gets hot. We're going to look at it from the outside and the inside. I've got it hooked up to 3 100 amp hour 12.8 volt LifePo4 batteries in series. Hopefully they can handle all this BS that I'm about to throw at this thing. We're going to try to break it. We're going to see if it's as tough as they claim and if any of the protections work. I'm going to try to give you the best review possible for this thing. I've also had ChatGPT analyze the circuit inside along with my own analysis. Stick around to the end and you will see all of this. You will see the pros and cons of this inverter, some of the quirks to it that I found over the past month and a half, what I like, what I don't like about it. At 3,500 watts, that is roughly around 30 amps, maybe 28 amps at 120 volts. Specific model is anywhere between $450 and $500, $600. I've seen them all over the place. On average though, they're around $500 to $550 for this. So this thing comes with a display, and it comes to like 10 or 12 feet of wire. You can mount this display really far. The display also has a remote on off. So basically we can turn the inverter off completely here, or we can turn it on and off with this button right here. So I'm actually using the cables it comes with. These are real copper. A lot of cheap inverters will never come with real copper cables. They will come with copper coated aluminum cables. This inverter boasts a bunch of protections: under voltage protection, over voltage protection. If your batteries get too low, it is supposed to shut off. If your batteries are too high, it is supposed to shut off to protect itself. It also has heat protection, thermal protection. Let's look at the connections here. Line 1 right here, we've got our neutral, we've got our line 2, we've got our ground. If we want to pull a full load from this, the full 3,500 watts, we can do it through these connections here or through this plug here at 220 volts. I don't think we can pull 3,500 watts from one side at 120 volts. We're going to test that and see today. This is for your ground if you want to hook it directly up to your breaker box. These terminals here are for hooking it directly up to your breaker box. I kind of like that. Here's our terminals, big beefy copper terminals here. You can see that, and when we open it up, you're going to see the copper. And this is a soft start. So there's a big resistor between this terminal and this positive terminal here. And when you go to initially hook this up and your batteries are all charged up and you don't want that big arc, you just hold your positive to this for a few seconds, and then you connect your positive to this terminal. Well, I didn't read the instructions when I first got it, so I had the big arc. This one boasts around 91% efficiency rating, and it is around 16 pounds, 3,500 watts. It is rather massive. I have bought other inverters in the past that are a tenth of this size that claim to be 3,500 or 3,000 watts, and they lied. Over the past month and a half, I've only had a 20 amp load on it at max. The display is showing us a good amount of information. It's showing us our battery level. It's showing us our battery voltage coming in. It's showing our voltage going out. It's showing our amperage, the temperature in Celsius. I don't think we can change that. It's showing the hertz, 239 volts. The thing I don't like about it is it shuts down very fast. That is obviously for efficiency. It's showing our status here. As you see, it automatically darkens if I don't keep tapping it. It's also a touch screen, and when you touch that, it just shows contact information if you want to contact the company or troubleshoot or do anything like that with them. I'm going to turn all these on at once and see what happens. Also, I'm going to get the thermal and see what's heating up with this thing. We're going to try to break it. All the outlets loaded with the biggest loads I could find. We're going to start kicking them on one by one on high. Everything is starting at once. Oh, on 3. Oh, I heard a fluctuation. Oh, it overprotection kicked. Let's see if I can start this on low. Okay, 6 amps. We'll put that on 2. Low. Oh, we're almost there. 13.5. Let's kick this one up a notch. We're right at the cusp of where it's going to cut off. We're actually exceeding, we're right on the edge, the limit of what this thing can handle. That's 30 amps. We're only supposed to be able to do 28 and see what happens. Let's see what's getting hot too. Okay, here's the thermal imager. Oh, it seems the cables are heating up. Yeah, we had a real hot spot just on the outside case. Oh yeah, let's see how many amps we're pulling. 111, wow! 4,000 watts going in. We got to add this amperage up right here. 16, 14, we'll call that 30 at 114. Total watts going in were 3,960. Total watts going out are 3,420. In order to find the efficiency, we have to take 3420 and divide it by 3960, which gives us 0.86. We multiply that times 100, so it's around 86% efficiency under full load. And you want to measure efficiency under full load. Now let's look at this sine wave too. Oh my God, how is that so perfect? Sine wave is actually pretty beautiful. I've got it hooked up. My oscilloscope, I've got it hooked up to these load lugs right here. I'm going to measure the other side now. Line 2, same. There is no deviation under this kind of load. That is insane. We've been around 20 to 30 minutes. I'm going to unhook it. I'm going to shut it down. We're going to tear it apart as fast as we can. We're going to see what's really hot in that circuit. These inductors are pretty hot. 160 degrees on those inductors. The big capacitors here are essentially blocking any cooling on those inductors. So those inductors are ripping hot. Now, maybe with the case on, that helps a little more. This is a fast switching diode. Okay, so this was our biggest concern. Right here, this is a fast switching diode. I was concerned that in this circuit design, that fast switching diode was taking the full load, 110 amps, and it's not. What else is hot while we can? Just the transformer. How hot are you? 147, 143. So the inductors here on the output, 2 of them. Is that just 2? The third one on the right isn't as hot as the front 2 here. But it could have been the way I had it hooked up. The MOSFETs look equally hot. They look like they're equally sharing the load. See that? It's hard to see through the thermal, but it looks like they're equally sharing the load. These film capacitors don't look very hot. The only troubling thing are these inductors. So what is most baffling and weird to me is that they used 1 transformer. That is more expensive for the manufacturer. You rarely see that. When you open up inverters, you usually see multiple transformers sharing the load. It's honestly significantly better for them to use 1 transformer, but it's more expensive because the smaller transformers are more common. You know, usually you see these small cookie cutter parts in these inverters. So that's a really good sign. Furthermore, it's better to have split phase through 1 transformer instead of 2 transformers. Beautiful, big, beefy heat sinks. I really like that they didn't use the case as a heat sink. They've kept it so simple. This is the simplest high frequency split phase inverter circuit I have ever seen, and I would almost gander that it's one of the simplest, and it was very expensive for them to manufacture. Just from looking at the transformer, the polyester film capacitors, that fuse, that bolt-on slow blow fuse right down there, and then they give you an extra one. It comes with an extra one. We've got another inductor here. This is a high frequency inductor. The only downside I can see from a thermal perspective are the inductors getting really hot. Why would they put these capacitors, these electrolytic capacitors, in front of these inductors? There's usually capacitors, especially electrolytics, cannot handle heat for very long or high ripple current. So these are specially designed to handle high ripple current, and they are meant for a very long life. They're more expensive capacitors as far as electrolytics are concerned. CD294 fans are really high quality. I like that. I like the brushless DC fan. The route they went is more expensive, you know, on almost everything I'm seeing here. with the single transformer, the film capacitors, especially that fuse. That's a really good sign. And then the extra fuse that is coming with the IGBTs on one side and then the MOSFETs on the other. I like that. I love the big, gorgeous copper bus bars here. I mean, you just never see that. I've never seen that. Not many of the other inverters. And then the simplicity overall, the conductor size. None of these conductors are aluminum. None of them are copper coated aluminum. I really like to see that. I mean, our conductor sizes are just right. Like that. I mean, everything is looking good here. All right, let's sum it up. Altogether, I think it's a decent inverter, a decent high frequency inverter. It depends on what you're going to use it for though. I would not run this thing at full capacity continuously. I would not run really high inductive loads on this. I mean, once in a while is okay, but not continuously. You know what this would be perfect for? This would be perfect for like a hot water tank. That's a resistive load if you want to use it on your hot water tank, or you're heating your house with electric baseboard or something like that. That's what this would be perfect for. But inductive prolonged loads, I'm not sure how it would handle that. The 91% efficiency claim, under full load, we didn't hit that. We hit 86%. Ran a total of 30 amps through this continuously for 20 to 30 minutes, and it performed okay. Voltage drop went down to 114 volts from 120. That is to be expected. That's really not that bad. What's most shocking about this inverter is that the sine wave didn't distort under that full inductive and resistive load, that nasty load we put it under. So would I recommend it? Yeah, I would, under certain conditions. Am I personally keeping this one? No, I'm not. I'm going to return this one because it's not right for me. It's not right for my application. I am doing a hybrid setup. That's what I'm switching to. So there was two situations in the last month and a half that happened specifically with me on this inverter. The one day I turned it on with no load and I had a random short circuit error message. I had a very moist environment in here that day, and I imagine maybe some moisture or humidity from the air is screwing with the ICs in this thing occasionally, but that was only on one situation. I had a short circuit message on the control, the display. It displays what's wrong, what the error is. I kind of like that too. And it was beeping nonstop. I simply shut the inverter off. I turned it back on. It went away. It hasn't done it since. There's a lot of moisture and dust in my air. So if you have any inverters or electrical equipment, you want to make sure to get that moisture and dust out of your air, because that can destroy electronics like this in a heartbeat. The low voltage protection didn't work for me on two separate occasions. My battery voltage for my lithium batteries dipped far below 30 volts with this, which this is supposed to shut off once it hits 30 volts. That didn't work for me. That being said, that was before I had my battery balancers hooked up on my lithium batteries. So maybe with the battery balancers hooked up, the low voltage protection will actually work right, but it didn't work right in my situation with this 36 volt inverter. Altogether, it's a robust, beefy, decent inverter. I am very surprised at some of the components, especially it being a cheaper split phase 3500 watt option. I mean, other options are what? Well past $1,000. You know, $800 to $1,000 for 3500 watt. Unfortunately, it's just not right for my applications, and I'm going to personally buy hybrid solar inverters that do everything in one. If you're going to run it at full load continuously with nasty, hardcore inductive loads, I don't anticipate it lasting very long. I'm not sure. But if you're going to run it at up to 80% efficiency, and you know, you're just running your small camper, RV, or house on it, and you're not running crazy stuff on it constantly, I think it would last for quite a few years, especially if you keep your air clean. You need to keep your air clean, and you need to keep the moisture in your air down. Is it a good bang for your buck? Yeah, ultimately, I believe it is. Hopefully you got something from this video, and if you did, please leave me with a thumbs up. It really helps the channel. If you have any questions, comments, concerns, put them down in the comment section. I hope you got something out of this. I really appreciate it. I'm very humbled that you did tune in and that you've watched the full video. Thank you. I will see you on the next one.